Okay, so we're going to take up the investigation. So the first part of the investigation looks at exponential functions of the form y equals b to the exponent x, where the value of b is greater than 1. So you're looking at values of b that are like 2, 3, 4, 5, 6, etc., or even 1.5, 1.7, doesn't really matter as long as the value of the base is greater than 1. So in the investigation you graphed, so you created a table of values and then you graphed three functions. And the three functions were y equals 2 to the exponent x, 3 to the exponent x, and 4 to the exponent x. Okay? And so one of the questions that you were asked to look at is, as x approaches negative infinity, what happens to the value of y? Okay? So what we're looking at is, as I look at values of x that get smaller and smaller and smaller, what happens to the value of y? Well, the value of y is decreasing, and it's decreasing towards a value of 0. Okay? So the value of y is approaching 0, which means as x is getting smaller and smaller and smaller, the value of y is getting closer and closer and closer to 0. Okay? One of the new notations that you're going to be looking at is a notation where you're using an arrow to indicate the words approaches. So, for example, all this really says is, as x approaches negative infinity, y approaches 0. Okay, so as x gets smaller and smaller and smaller, y gets smaller and approaches 0. Okay? Okay, and so we can see that all three of the functions that we drew get closer to y equals 0, but they never touch it. Okay, the next question says, using this information and prior knowledge, what can you add to your graph? Now, if we think back to what happens when you're sketching a graph and the graph approaches a value but never touches it, what we looked at was something called an asymptote. And in this case, we have a horizontal asymptote since the graphs are getting closer and closer and closer and closer to a value but never touching those values. So what we can add to this graph is a horizontal asymptote at y equals 0. And I'll add that in right now so we can see it. So I know it might be hard to see, but there's a horizontal asymptote at y equal to 0. Okay? So remember, when we're drawing horizontal asymptotes, we use a dashed line. Okay, so a dashed line to represent the horizontal asymptote. Okay, so the next question is, as x approaches positive infinity, what happens to the value of y? So what we're trying to figure out is, as I increase the value of x, what's actually happening to the value of the function? So we'll notice that all the graphs seem to be going up and to the right. Okay, so as the values of x are getting larger and larger and larger, the value of the function is also getting larger and larger and larger as well. And so what that tells me is, this function is increasing, and what it's increasing towards is positive infinity. As I plug in larger values of x, the values of y get larger as well. Okay, so the value of y approaches positive infinity, or in other words, as x approaches positive infinity, so as x gets larger, y approaches positive infinity. Y also gets larger. Okay, next part asks us for the domain and range. Now the domain and range here is a little bit different, and the domain of the function, if you look at the graph and you think about how far to the left and to the right the graph can extend, in terms of how far to the left the graph can extend, notice that there is no limitation on what the smallest value of x can be, and there's also no limitation to how large the value of x can be. So what that tells me is the domain is all real numbers. But in terms of the range, there is a limit to how low y can go. Okay? Notice that y is not negative. Okay, it'll never be negative unless there's some transformations applied. But you'll also notice that y is not equal to 0, and that all the values of y that we have are actually positive values. So what that tells me is y always has to be greater than 0, and y is an element of all real numbers. So that's what we know so far. The range is all real numbers, the domain is all real numbers, and the range is all real numbers such that y is greater than 0. Okay, the last part says, how does the graph of an exponential function vary as the value of the base increases? So now let's take a look at the graph to help us answer this question. So here's our three graphs, and you'll notice that for y equals 2 to exponent x, 3 to exponent x, and 4 to exponent x, the graph seems to be getting steeper. And I don't want to say steeper in the sense that it's like a linear function, but if you think about in the sense that how fast the graph is growing, the graph is actually growing much faster for the green graph, which is y equals 4 to the exponent x, versus the blue graph, which is y equals 2 to the exponent x. And the reason why that happens is because you're multiplying a much larger number between 2 and 4. You're multiplying a much larger number by itself more and more times. So if you think about what y equals 2 to the exponent 2 is versus y equals 4 to the exponent 2, so the same value of x, I used x equal to 2. For the same value of x, y equals 2 to exponent 2 only gives me an answer of 4, whereas y equals 4 to exponent 2 gives me an answer of 16. So I get a much larger value much faster. So what happens is the graph of the function gets steeper since the rate at which the function increases is larger. So I'm increasing by a rate of 4 for y equals 4 to the exponent x versus a rate of 2 for y equals 2 to the exponent x.